Well, it's a great personal privilege for me to introduce Danny, because I first met Danny during the academic year 1970 at the Technion, where he was finishing his PhD thesis at that time. And we wrote a short conference paper together, 2 pages long, okay? And I completely forgot about it until you won the Nobel Prize. So he had all his education at the Technion. After he did his military service, he did in sequence first a bachelor's degree in mechanical engineering, the real world, and he then proceeded to do his MS and PhD degrees in materials engineering, not material science and engineering, but materials engineering. And he was one of the first people in Israel, first material scientists and engineers, to use electron microscopy to study hard materials. Most of the work in Israel using electron microscopy had been done by the life scientists studying soft materials. And so, you know, he was in a vacuum, so to speak, almost initially. It was a real pioneer just in the use of classical electron microscopy. And what he won the Nobel Prize for, as many of you know, is, I would say, the discovery of this quasi-crystalline state of matter. So that's a real discovery, and it's a real paradigm shift, as he says in his, the title of his talk. And he discovered this in the year 1982, well, on a sabbatical at what was then called the National Bureau of Standards, which is now NIST, using classical transmission electron microscopy, as he'll tell you. And then it came time to write the research up, and he did write the research up first with a colleague of his at the Technion, who's an expert at diffraction, X-ray diffraction, Ilan Blech, and they submitted it to the Journal of Applied Physics, and it came back not of interest to physicists. So they then submitted that paper to a very conservative journal, Metallurgical Transactions, and it took a long time to get an answer. In the meantime, with 2 colleagues of his with Ilan Blech and also with John Kahn, and then a 4th author joined, a Frenchman, Denis Gracias, joined, they submitted it to the Physical Review Letters, and physicists like new things, and it went flying through, and it was published in late 1983. And then the subsequent paper appeared in Metallurgical Transactions, which was a model of what the quasi-crystalline state looks like. And then you would expect everyone to stand up and clap, and that didn't quite happen. There were a lot of naysayers, as he'll tell you, to this discovery. And so it took a long time to get the Nobel Prize, 2011 to be exact. So it didn't happen instantaneously. And I said this yesterday, but I'll say it again. I was on a stationary bike or a Nordic track at that time in my basement, listening to the news, NPR, and they announced the prize. It's about this time, a little bit earlier, October 2011. And it didn't sink in at first. It didn't sink in. And then I said, oh, he won the Nobel Prize. Incredible. And I sent you an email letter, I'm sure, pretty quickly. So he's going to talk to you about the discovery today of this quasi-crystalline state of matter. Okay, I think I've said enough at this point.
Okay, thank you very much, David, for this introduction. So now I will tell you the second half of my talk. He gave the first half. No, okay. So one more thing about me, and some of you know it already. This is the most important thing to know about me, besides what David said, is that I have 10 grandchildren and 4 children and 1 wife. So now you know everything. Okay, so in order for you to understand the background for the discovery, let me take you back to the mid-'80s. And in the mid-'80s, there were 3 surprising discoveries of the structure of matter and its properties. And these 3 discoveries came year after year, and all 3 of them received the Nobel Prize, which is quite remarkable. So the first one, chronologically, was the discovery of quasi-periodic materials. This is the subject I'm going to talk about. And the names on that are my name and Ilan Blech, Denis Gratias, and John Kahn. And the paper was published in 1984. Discovery was made in 1982. Paper was published in 1984. I'll tell you the story, what happened. Second came the discovery of fullerenes, Harry Kroto and his colleagues. And a year after that, high temperature superconductivity. Now, when high temperature superconductivity was discovered, everybody was happy. It was a real discovery. I mean, of course, superconductivity was discovered in 1909, many years before that, but people did not quite expect high temperature superconductivity. So when that discovery was announced, everybody was happy. When Harry Kroto and his colleagues talked about fullerenes and the football structure of fullerenes, the model met some opposition, but that opposition died very soon. However, when our discovery was announced of quasi-periodic materials, it met a lot of opposition. And it came from the top of the scientific community. And that opposition lasted for 10 years. Or it was a fierce battle, and I will tell you what happened and how the balance shifted between believers and non-believers. So let's start. But in order for you, for everybody, including the lawyers among you, to understand my talk, I will briefly explain several basic facts. And I will talk about order in crystals, I will talk about periodicity, and about rotational symmetry. Once you understand order and rotational symmetry and periodicity, then you have the background to understand the discovery. So let's start with order. Here is a two-dimensional lattice. Let's say these are atoms. Every motif is one atom. And clearly you see that there is order here. What does it mean to you? It means that if I ask you to continue this in this direction or in this direction or in any direction, you know how to do that. Right? It's very simple. You know how to continue it. That's the order that we have here. This structure is not only ordered, it is also periodic. And there is periodicity in each and every direction. For instance, in this direction there is periodicity. In this direction, periodicity. In this direction, the distance between every two atoms is the same in each and every direction. The distance itself changes, but the periodicity is there in each and every direction. That's periodicity. Now, in this case, the motif is one unit, one atom. But the motif can be more complex. The motif can be something like a molecule. And here is an example of that. This is the picture of a fence of my hotel in Easter Island. So you see the ocean right behind it. And here there is also periodicity. But the motif is not just one bar, it's several bars. So look here on the left. You see this combination of bars? It's large, large, small, small, large, large, tiny, small, large, large. This is the motif, right? And it repeats itself. Again, exactly the same one, and again, and again, and again, and so on and so forth. This is a one-dimensional periodicity, and the motif is not just one bar or one atom. It's like a molecule. It's several units together. So it can be one atom, it can be more complex. That's about periodicity. Now, here is a motif which is much larger. This is the ribosome, and Ada Yonat and her colleagues received the Nobel Prize for deciphering the structure of the ribosome. It contains thousands of atoms. And in order to study the structure of ribosome and to know where every atom is in a very complex structure, Ada Yonat had to make a crystal out of this ribosome. She had to crystallize the ribosome. That took her 15 years to do. But eventually, she did something like that. And once she had a crystal made of this ribosome, she could take it to a synchrotron and study the position of each and every atom. This was a remarkable achievement, but it's based on crystallography. In recent years, crystallography changed dramatically. Instead of studying the structure of matter, they study the structure of molecules by creating crystals from these complex molecules. So this is the direction in which crystallography goes. Now let's say a couple words about rotational symmetry. Here I drew the same two-dimensional lattice, but I added a red handle at the top so that you see what happens when I rotate it, and I can rotate it 90 degrees, 180 degrees, 270 degrees, 360 degrees, and it looks the same. Every time it looks the same. So this is why this structure has a 4-fold rotational symmetry. You can do it 4 times, and each time it looks the same. Right? So this structure has a 4-fold rotational symmetry. Here are several examples. This card on the left has a 2-fold rotational symmetry. You can turn it 180 degrees, and it will look the same. So you can do it 1, 2, twice. It has 2-fold. This set of triangles has a 3-fold rotational symmetry. The flower has a 5-fold rotational symmetry. The pizza has a 6-fold rotational symmetry. These are motifs. Motifs can have any rotational symmetry that you want. There's no limitation to that. Okay. Let's say a few words about crystallography. You know, you can go back to the ancient Greeks and say they understood crystallography because they had good ideas about structure of matters. They invented the term atom that cannot be divided. Well, now we know we can. But it was a good concept of something that's very small and cannot be divided. And because they looked at crystals that they have found in nature, and the crystal had facets and certain shapes, and sometimes different compositions had the same shape, they concluded that the little atoms inside are arranged in a certain way. And everything was correct. But they did not have any way to prove what they thought was correct. Now, if you look at science and the development of science, many people will tell you that the ancient people knew a lot about science. They did not. You can always find a thread of truth if you go back, but the nonsense that they had in their minds is unbelievable in each and every direction that you think of. So although you can thread back, go back and find some logic in science, science really started, let's say 300 years ago or so. Before that, there was almost nothing. But they had a good idea. In 1895, Röntgen discovered the X-rays. And for 12 years until, for 17 years until 1912, nobody knew what X-rays were. They used X-rays to look at fractured bones immediately after the discovery. A year after the discovery, you could buy X-ray machines to look at the inside of the body. But nobody knew what X-rays were. Von Laue, a German scientist, performed in 1912 a fantastic experiment. He made a diffraction pattern, X-ray diffraction pattern from a crystal. And he proved in one experiment that X-rays had a wavy nature, electromagnetic waves, and he proved the crystals are indeed what people thought, made of atoms, and the atoms are arranged. They are ordered atoms in a crystal. But von Laue also found that his crystals were not only ordered, it was also periodic. And for 70 years, between 1912 until 1982, all crystals that have been studied were ordered and periodic. There was no one exception. Hundreds of thousands of crystals were studied by tens of thousands of eminent crystallographers, precision work, excellent X-ray crystallography. All crystals were ordered, therefore crystals, and periodic. And so over the years, a paradigm was accepted that crystals are ordered and periodic, and this was the definition of a crystal. So let's continue. We can skip the story. I told you the story. And crystal definition until 1991 was something like this. This is from a book by Quality X-ray Crystallography, X-ray Diffraction. And it says the following. This is a nice definition. Very simple. A crystal may be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. Ordered and periodic. This was an atom. This was the basis of understanding of crystallography. Another definition, different words, exactly the same meaning. This is the book, from the book Structure of Metal, Barrett and Masalsky. Atoms in the crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Exactly the same thing. This was the definition. Now, when the science of crystallography started in 1912, almost immediately a large, growing group of crystallographers was developing the science. By the way, a year after, in 1913, Bragg, the father and the son, developed the Bragg equation, and from there on, we had a science that was fast developing. The X-ray machines became more and more accurate, and people trusted X-ray diffraction. A society was formed called International Union of Crystallography. An International Union of Crystallography was in charge of saying what is right and what is wrong in crystallography. The governing body of International Union of Crystallography are mathematical crystallographers. These are hardcore mathematicians. These are no-nonsense people. These people demand definition from the very foundation. Everything must be approved from the very foundation of mathematics. They rule the science, and the tool of choice was X-ray diffraction. Not electron diffraction, that was not accepted. Neutron diffraction, forget it. X-ray diffraction is the tool we trust. And that was it. Okay. So, crystallography in 1982 is the year of the discovery. Can be, I can give you an example of what we studied at that time. A book by Kittel, by Charles Kittel here. And of course, you cannot see because this is written in very small letter, what is marked in green. And this is why I have magnified it for you, and now you can see. So it says the following. We can make a crystal for molecules which individually have 5-fold rotation symmetry. But we should not expect the lattice to have 5-fold rotation symmetry. Every molecule can have any rotation symmetry that you want, but not the lattice. The lattice cannot have 5-fold rotation symmetry. Okay, why so? Here is an example of a proof that you cannot have that. But there's a story that goes with it. When I did my master's degree at the Technion, I took a class in crystallography. And in the final exam, one of the questions was, prove that crystals cannot have 5-fold rotation symmetry. And I proved it. And I passed the exam. And this is why I'm here now. So let me show you one way in which you can prove that 5-fold rotation symmetry cannot exist in crystals. So here goes. Take 2 atoms, P and Q, and choose them in such a way that the distance r between them is the minimum distance in that particular crystal. Okay, so the r is the minimum distance between 2 atoms. Now, if 5-fold rotation symmetry is allowed, is possible, then you can rotate Q around P 5 times and P around Q 5 times. Let's see what happens when you do that. Okay, so here is Q right there. Okay, 1, 2, 3, 4, and 5, and we should have a Q prime atom here. This is the 5-fold rotation symmetry is allowed. Now, what about P? Here's P, 2, 3, 4, 5, and we should have a P prime atom there. But the distance Q prime, P prime is shorter than R, as you can clearly see, and this is impossible because we chose the 2 closest atoms. Okay, no 5-fold rotation symmetry in crystal, and the science of crystallography was a mature science. Mature science is a science in which you don't expect any revolution to happen. We understand everything, said the International Union of Crystallography. Yes, you can find new structures, new minerals, and you can decipher the structure, but the structure is known. Let's say that you find a new alloy or a new intermetallic with a structure of DO19. Wonderful, with a drawer of 2051 crystals with DO19 structure. Welcome, 2053. Welcome here, close the door, and the world is happy and quiet. Okay, no problem. Now, let me show you how atoms look in a periodic lattice. These are carbon atoms in diamond. These pictures that I took many years ago. And every white spot is an atom, and clearly you can see that it is not only ordered, it is also periodic. And there is periodicity in this direction. You see the yellow line there. And in this direction, and in this direction. Any direction that you choose, you see that there is periodicity. You go along a line, you see that there is periodicity. And the rotation symmetries that are allowed in periodic crystals, and all crystals were periodic. The allowed symmetries are 1, 2, 3, 4, and 6. No 5, and nothing beyond 6. Nice. Okay. Now, let me take you now to the reciprocal space. This is a space in which the diffraction patterns exist. And here is, this is, by the way, an electron diffraction pattern, and taken from a periodic crystal. And the diffraction pattern is also periodic. If the crystal is periodic, so is the diffraction pattern. So what you see here is this fat spot in the center is the transmitted beam, and all the other spots are diffracted beam. What you do in an electron microscope, you shine an accelerated beam of electrons onto a specimen, and the specimen is very thin. It's very thin because you made it very thin. And part of the beam goes through, and this is the central beam. This is the transmitted beam. And other parts are elastically scattered to form a diffraction pattern. And these are the rest of the spots, okay? And there is some more to it, but we are not going to dwell on that too much. So this is a diffraction pattern from a periodic lattice. And you see that there is periodicity here. The rotation symmetry of this crystal is also 1, 2, 3, 4, and 6, much like in the real space. And 5-fold rotation symmetry is not allowed. And you see, too fast, too fast. Come back, come back. Okay. So you see periodicity in this direction, and periodicity in this direction, and periodicity in this direction. So you take any distance between the central spot and one diffracted spot, you multiply it by any integer, say 2, you see that there is another spot. Distance from here to here, multiplied by 2, you're here. Multiplied by 3, you're here. Multiplied by 4, you're here, and so on and so forth. All right? So there's periodicity, and everything is nice and clean and no problem. And then something shockingly happened. In 1992, the definition of a crystal has been changed. This is a definition that was created by the International Union of Crystalography. These are the non-nonsense mathematical crystallographers. And they have issued a new definition of a crystal. And this definition is so wonderful, it is like a poem. We will read it slowly, and you will see why it is a poem. Let's see. It doesn't say a crystal is. No. It says by crystal we mean. See? By crystal we mean any solid having an essentially discrete diffraction diagram. Not a difference. No. Essentially discrete diffraction diagram. And by aperiodic crystals we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Now I'm asking you, is it not a poem? You remember the old definition? A crystal is ordered periodic. That's it. No. This is a wonderful definition because it is a humble definition. We are not sure anymore. We are open to learning something new. Now, after 70 years, if somebody is open to learn something new, That's an achievement. So what happened? Why did we need to change the definition of a crystal? We needed to do that. This was International Union of Crystallography. Okay. This was the cause of the discovery of quasi-periodic materials, and now I'm going to tell you about the discovery. Up to now, it was an introduction. 1982 was the 70th birth of crystallography, and this was the year in which quasi-periodic crystals were discovered. Now, in order to take you back to my laboratory in the day of the discovery, let me show you a page in my logbook from that day. The lesson to the students here is that when you make an experiment, write it down in a logbook. You may remember the experiment up to the next week, but beyond the next week, you forget what you did if you don't write it down in a logbook. Write down every experiment in a logbook. In most cases, it's not important. In some cases, it's crucially important. Write it down. So here's that page. Now, I have to explain. This is my electron microscope logbook, and this is the page. And the day, you have a lot of information here. Although it's written in a sloppy way. It was not written for you. I would have made more effort to write it nicely. But it was written for me. Nobody was supposed to look at it, ever. It just so happens that you do. So it has the date, April 8, 1982. I was working on aluminum 25 weight % manganese. This was a rapidly solidified alloy. It doesn't mention here because all these years I was working on rapidly solidified material. And this number, 1720, is the plate number in the microscope. So there were many before and many after. So 1720, 1721, and so on and so forth. SAD is selected area diffraction pattern. Selected area diffraction. It's a diffraction pattern in an electron microscope. And then plate number 1723 is 17K, which means it's a picture, not a diffraction pattern, it's a picture, with 17,000 magnification, 17,000 time magnification, and then 36,000 time magnification, and this is plate number 1724. Now, when I look at plate number 1724, I look at the microscope and I say, what's going on here? That's interesting. Now, as you remember, when Archimedes made his discovery, he jumped out of the bathtub and shouted, "Eureka!" We don't do that anymore. First of all, hardly ever we have time to take a bath. We take showers, right? We don't sit in the bath. We take showers quickly. And number two, nowadays, when you see something which may be a discovery, you say, that's interesting. What is this extra peak? Or what is this? What's going on here? That's interesting, right? And then that may be a discovery. So I look at this picture, number 1724. I will show you this picture. And take a diffraction pattern immediately. Plate number 1725. I will show that to you too. And I write down 10-fold rotation symmetry with 3 question marks. It cannot be. I just told you it cannot be, right? Okay. And then I continue that afternoon to do all these experiments to find out what I have. I will tell you what I thought I had, and I will explain these experiments later on. This set, the first set of experiments, you see all these are connected. It means that I'm working on one crystal. All these pictures were taken from one crystal. And then I move to another crystal here, and so on and so forth. Okay. All these are dark field images. DF are dark field images. It means the following. Here is a part drawing of the diffraction pattern, part drawing of the diffraction pattern. And if I use, this was plate 1727, I use this diffracted spot to look at the image. So it is called dark field. If you take the central spot to do the image, it's called bright field image. Okay. But the purpose of this experiment was to find out what I have there. And what I thought I have there are twin structure. I will tell you what twins are shortly. Of course, we have some experts on that here, but most of you don't know that. I'll tell you what twins are shortly. So I continued that, and everything happened in that afternoon. I know it happened in the afternoon because the page before that is the same day in the morning. So in the morning I was working on one alloy, and in the afternoon on another alloy. Later on, the Nobel Committee says that it's very rare they can pinpoint the discovery to a certain hour of a certain day. Usually a discovery takes a long time to analyze and so on. But this was discovery, you can trace back to that. OK, so let's continue. This was it. This was the discovery, right here, tenfold. This is plate number 1724. What you see here is the following. This is one crystal. See? Here's another crystal. This is a polycrystalline material. It has many crystals in it. Here's another crystal. Here's another one, and so on. This is the size. So each crystal is about half a micron. Okay? These are small crystals. Some of these crystals, like this and this and this and this and these, are pitch black. And this is what was so interesting. And this is bright field image using the central beam. Why is it so different? I have never seen before such a black crystal. It means that most of the energy goes to the diffracted beam. It diffracts heavily. So much so that the central beam, the transmitted beam, has almost no intensity in it. And I have never seen any material that diffracts so heavily before. And I was a veteran electron microscopist at that time. So I had a lot of experience with electron microscopy. So I look at it and say, wow, what's going on here? Let me take a diffraction pattern. So I took a diffraction pattern from this crystal only, and this is how the diffraction pattern looked like. So I look at the diffraction. This is it. This is the original picture. It's not something that I took later. This is the picture. So I look at the picture. I look at the diffraction pattern, and I say, hey, what's going on here? See, first of all, what is the rotation symmetry? So I start to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, cannot be. 1, 2, 3, 4, 7, 8. And I write tenfold with 3 question marks. That's not all. You see, there is no periodicity in this diffraction pattern. So take this line, for instance. Right? Take the distance from this spot to this spot, and multiply by 2, you get here. And there is nothing there. No periodicity. Tenfold rotation symmetry, no periodicity. Very strange. Very strange? Not quite, because I thought I knew what I had there. I'll tell you what I thought. It was wrong. I couldn't find what I thought. But the distance from here, let's go here. OK. The ratio of distances from this spot to this spot divided by this from here to here is the Fibonacci number tau, which is 1.618, and it's an irrational number and endless number of digits beyond it. OK, so this is how it's also called the golden mean. It means that some people think that the Fibonacci number 1 plus root 5 divided by 2 has a static value. So if you measure the distance between the forehead and the nose and divide by the distance from here to here, if the person is very beautiful, then it has this wonderful ratio, and so on and so forth. Don't argue with people that tell you that they believe in aesthetics. It's in the eyes of the beholder. OK, so this was quite strange. And I said, OK, what I have here are twins. By the way, the rotational symmetry is not tenfold, as you can see here. It is fivefold. But that could be seen only later on when I took another diffraction pattern called Kikuchi pattern. And on the Kikuchi pattern, I could see that it was fivefold. It doesn't matter. Fivefold, tenfold, both are forbidden. OK, so I started to take more diffraction patterns. That means the following. Let's say that this is my crystal. In the electron microscope, there's a goniometer. It means that I can tilt the crystal, and I can rotate the crystal in the electron microscope. And I can take diffraction pattern in this position, in this position, in this position, in that position. I can take many diffraction patterns. And this is the set of diffraction patterns that I took from that alloy. So this is the fivefold rotation symmetry, twofold and fivefold again, and 5, 3, 2, 3 here. And this set of diffraction pattern has an icosahedral symmetry. Later on, I'll tell you what is an icosahedron. OK. And then what did I think? I thought I had twins. And let me explain to you what twins are and why did I think that I had twins. This is based on my previous experience. OK, so what you see here, these are carbon atoms in diamond. And this is a real picture. You see here, this is just a model, computer model. It's just a copy of this, but done on the computer. So what you see here, this is a single crystal right here. See, it's ordered and periodic. This is another single crystal, another one, another one. There are 5 of them, 5 single crystals. And there are boundaries between them. But the boundaries are not just any boundaries, arbitrary boundaries. They are twin boundaries. It means the following. Look at these 2 crystals. Let's say look at this and this. See this plane of atoms? It continues here. So the boundary is like a mirror. It creates like a mirror image, right? And from here to here, another mirror image. And from here to here, another one. And from here to here, and so on. So these are twins. Now, when you take a diffraction pattern from one of them, from here, you will get a periodic diffraction pattern because the crystal is periodic. OK, nothing special. But when you take a diffraction pattern from all 5 of them together, take a diffraction pattern from all of them together, then you will have 5 superimposed diffraction patterns, rotated 360 divided by 5. 36, one here, one here, one here, one here, and so on. And 360 divided by 5, 72 degrees between each one of them. And obviously, it will have a 5-fold rotation symmetry because it's a combination of 5 diffraction patterns. This is what I thought. So I said to myself, OK, find the twins, record them, and forget it, because it's not interesting. I spent the day looking for the twins, performing several experiments. No twins. Couldn't find the twins. So on day 1 of the discovery, I knew what I don't have. I didn't have twins. I didn't know what I have, but I knew what I don't have. Why is it important to say? Because many scientists claimed years after that these are twins in periodic crystals. I knew from day 1 that no twins. I was convinced, no twins. I see the atoms. How can there be twins? OK. So forget the sigma notation. OK, so this was one example. Here is another example of another crystal, again with 5-fold rotation symmetry. These are pictures, by the way, of an alloy of an intermetallic between iron and aluminum. And in aluminum iron alloys, they are abundant and they are large. They are quite large. So you find them, many of them, you find them. And these are pictures that I took many years ago. And there's a story behind it. I took these pictures, and I took a diffraction pattern from each one of them and buried it in the drawer because I found it not interesting. Later on, colleagues of mine in Sweden, I found, published 5 papers on this picture. I thought it was trivial. Why publish it? You have to learn. OK. So here we have 10 twins. Look at the petals of the flower. There are 10 of them. 1, 2, 3, 4, 5. There are 10 of them. Each one of them is a single crystal. And the boundaries are twin boundaries, much the same as before, as I've shown you before. So if you take a diffraction pattern for one, it will be periodic. If you take diffraction from all of them, it will have 10-fold rotation symmetry. But really, it will have 5-fold because the orientation of this crystal is exactly the orientation of this crystal. And the orientation of this is exactly that. So there will be 5 of them. Anyway, this is what I thought I have. And this is the combination diffraction pattern that you get. But this is a combination of 5 of them, and here is just 1. Okay? This is 1, which is periodic. And you have 5 of them rotated to each other. OK, let's continue. So I did also dark field experiments. I'm not going to dwell on that. It's too professional. It's not for a general audience. But I could not find any twins. I did also micro-diffraction called CBED, convergent beam electron diffraction. What you do there is you converge your beam in an electron microscope into a very small spot, and you take a diffraction pattern from that spot only. And if there are twins, then the twins must be smaller than that spot. And the size of that spot on that microscope was 400 angstrom, 40 nanometers. If there were twins there, they were smaller than 40 nanometers. Very unlikely. Okay, we'll also skip this experiment, although it's quite interesting. This is a more modern picture of the icosahedral phase, and you see beautifully the motifs here, but no periodicity. See, tenfold, 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 endless number of tenfold, but no periodicity. Okay, so this was up to 1984. I'll tell you what happened when I talked about my discovery. But in 1984, at the end of 1983, I came back to the Technion. And there I found the first person who was willing to work with me. His name is Ilan Blech. Ilan Blech was a professor at Technion. And shortly after we published the first paper, he left the Technion to do business in California and succeeded doing that. And from there on, he's there. But we sent this paper for publication. And as David Zeiman said, we sent it to a Journal of Applied Physics. Those days, I'm talking to the young among you, scientists could not type. We didn't type. We wrote our papers by hand, and we had a secretary to type our papers. And we thought that secretaries are there to type papers. This is what they did. And every time we correct, they typed it, they printed it, we corrected it, we gave it back, they typed it again from the very beginning, and we corrected it, they typed it again from the very beginning. It was toil and trouble. But that's the way we did it. And then so I had this paper printed after it was typed on the typing machine, and I put it in an envelope, stamp on it, wrote nicely the address of Journal of Applied Physics, and sent it by the mail. 2-3 weeks later, I received the paper back in another envelope, and it says, "Dear Dr. Shechtman, thank you so much for your contribution. However, the editorial board of Journal of Applied Physics has decided that we are not going to send it for review because it will not interest the community of physicists." "Why don't we send it to a metallurgical journal?" they advised me. So I said, okay. I put it in another envelope, wrote nicely the address of metallurgical transaction, stamp, send it, and they accepted it. And they accepted it at the end of 1984, but they published it only in June of 1985. This is slow publication. Okay. In the meantime, in the summer of 1983, I came back to Nice, and I told John Kahn that my paper was rejected, and I sent it to Metallurgical Transaction. And "Why do you think it was rejected?" I asked him, and I gave him the preprint. He read the preprint, and he said, "Oh, Danny, this is blah, blah, blah." We had some arguments, and finally he said, "Oh, this is fantastic. Why don't we do something totally different? Let's send it for a quick publication, and let's invite also Denis Gratias, who is a mathematical crystallographer from France." John is a thermodynamic person, John Kahn. And so we invited Denis Gratias. We wrote a shorter paper without the Ilan Blech model. Ilan Blech was a nice physical model, and it is in the first paper that was sent, but it is the second that was published. And we sent the paper to PRL. Paper was accepted very quickly and published at the end of 1984. So this is the first paper, and this is the second paper. And when this paper was published in November 12, 1984, hell broke loose. Because immediately I started to receive email and telephone calls from scientists I never heard of from around the world. "Danny, we have it, this is fantastic." And very quickly, an eminent avant-garde group of young scientists around the world grew dramatically, very quickly, and started to study quasi-periodic material. They copied my experiments within a week. It was easy to copy them. Anybody who could rapidly solidify materials did that. Very easy. They got the same results. And that community grew very, very fast. And they were physicists there, material scientists, chemists, mathematicians, architects. Architects liked the Penrose tiles, and so on. Okay, so this was the second paper. What is an icosahedron? I talk about icosahedral symmetry. What is icosahedron? This is an icosahedron. It's a platonic body, and it has, it has 6 5-fold axes, 10 3-fold axes, and 15 2-fold axes. The way you look at it right here is a 3-fold axis. When you rotate it, as we see, 1/3 of a turn, it will look the same. Another third of a turn, it will look the same. If you look from here, from above, up here, down through this point to the center, you see that there is 5-fold rotational symmetry, and 5-fold here and here, so 6 of them, and so on. This is icosahedron. So the set of diffraction patterns that I have received from the icosahedral phase, we call it icosahedral phase because it has icosahedral symmetry. It has exactly the same 5, 3, you see, 5 from here, 2, 3, and 5 again, 5, 2, 3, and 5 again, and so on. This is why we call it icosahedral symmetry. Another way of seeing an icosahedron is looking at a football. This may be easier. See, this is football are made of patches of pentagons and hexagons. I'm sure all of you know you have a team here. A team of football here? Soccer, right? Okay. So, okay. So you see nicely the 5-fold symmetry here, and the 2-fold here, right? 2-fold, and 3-fold here. And I doubt that the football players know that they play with icosahedral symmetry. I sort of doubt it. But anyway, so this is the icosahedron. Now, so what is quasi-periodicity? In order to understand quasi-periodicity, let me take you back to the 13th century, and I'll have you meet Mr. Fibonacci. Leonardo Fibonacci de Pisa was the greatest mathematician of his time, and probably several hundred years later, he was still the greatest mathematician. So here he is. This is the painting of young Fibonacci de Pisa. His friends called him Blockhead. I don't know why. He had a very bright mind. I call him Blockhead. And this is a picture, this is a real picture of a statue that is erected in his memory. And you know where it is? Many of you have been there. It's in Pisa, just behind the inclined tower of Pisa. Just about 50 meters behind it, there is a graveyard under a roof. It's a building which is a graveyard, and it's open to the public. And this statue is there. I couldn't find his grave, but the statue is there in his memory. So if you visit the inclined tower of Pisa, it's worth going 50 meters behind it and find this statue in honor of Mr. Fibonacci. Say hello for me if you are there. Okay. Now, in order to understand quasi-periodicity and how Fibonacci is related to quasi-periodicity, let me tell you something about Fibonacci rabbits. So what are Fibonacci rabbits? So here are the Fibonacci rabbits. Here is what you see. And Fibonacci said the following. Let's say that we have a female rabbit. And in the first month, here she is. She has a husband or a boyfriend. He comes to visit, and now she's pregnant now. And in the next month, she gives birth to a little one, to a little rabbit. Okay? In the third month, the same thing happens, and this mother gives birth to a little one. This little one matures. It doesn't reproduce yet. Right? It matures. In the fourth month, this mother gives birth to a little one. This one matures, and this mother gives birth to a little one. So these are the rules. Once you understand the rules, you can continue this forever. That's it. Okay? There is order there. You know the order. You can continue this. But let's look at these numbers. These are called the Fibonacci series. 1, 2, 3, 5, 8, 13, 21. What is these numbers? 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8, 13. 8 plus 13, 21. 13 plus 21, 34. 21 plus 34, 55, and so on. These are the Fibonacci. This is Fibonacci in the series. And these are the number of rabbits in each month. You can count them. Okay. So what about quasi-periodicity? There is order, but what is the quasi-periodicity? Look here. We have large rabbit, small, large, large, small, large, small, large, large, small, large, large, small, and so on and so forth. There is no motif of any size that repeats itself periodically. There is order, and the order is quasi-periodic. It's quasi-periodicity in one dimension. So Fibonacci series is quasi-periodicity in one dimension. Now that we are having dinner with Fibonacci, let's say a few more words about him. So an equals an minus 1 plus an minus 2. It means that 1 is 3 minus 2, and so on, and 3 plus 5 is 8. This is what this means. And now, if you go to infinity, if n goes to infinity, if you continue this list forever, and you can do that if you have time, then the number of rabbits in the last line divided by the number of rabbits in the line previous to that is 1 plus root 5 divided by 2, which is 1.618 and all that. And this is the Fibonacci number tau. So it's an irrational number tau. OK. And Mr. Fibonacci published it in the year 1202 in a book called Book of Abacus, or in Italian, Liber Abaci. Now, for the sake of history, I must mention the following. The book was not meant to talk about the Fibonacci rabbits. It's a little chapter on the side of the book. The book was about the Indian Arabic numerals that he tried to convince the merchant of Pisa to use instead of the Roman numerals that they were using. It was very difficult to do math with the Roman numerals. And it is very easy to do with the Indo-Arab numerals. So this is the book. This is what he was trying to do. And he showed, OK, here is when you add two numbers. See how easy it is? And here when you subtract. And here is when you multiply. And here is when you divide. This was the book about, Liber Abaci. And this is a side chapter in that book. But this is the beginning of quasi-periodicity. I doubt that Fibonacci knew about quasi-periodicity. But this is what he did. What about quasi-periodicity in 2 dimensions? Fibonacci 1 dimension. 2 dimension, Penrose. What are Penrose? Eminent scientist living in our times in England. He's a physicist. He's a thinker. He's a wonderful, tremendous scientist. And he invented the Penrose tiles. These are 2 tiles with these are 2 rhombi, 36 degrees, 72 degrees. And if you join them according to certain matching rules, there's a rule how to join them, then you will get this Penrose pattern. It fills the space. If you take a diffraction pattern from this, you'll get a 5-fold rotational symmetry diffraction pattern. As another scientist showed, his name is Alan Mackay. He's a crystallographer from England, also living in our times. And so this is quasi-periodicity in 2 dimensions. So Fibonacci, 1 dimension, Penrose 2 dimensions. What about 3 dimensions? Well, 3 dimensions are quasi-periodic crystals, and the atoms here are arranged in a quasi-periodic way in 3 dimensions. You see nicely the 5-fold facet and so on. OK, so now I would like to show you something. And I will ask you to think. Too much? Let us think together, OK? Let's pay attention to what I'm taking. This is not a story. This is something that I want you to understand. And this is called the cut and project. And what we do with the cut and project method, we take a high-dimensional space. We make a cut and project in that space onto a lower-dimensional space. And from a periodic lattice, we will receive a quasi-periodic lattice. I know it sounds complicated, but it is so simple, you will laugh. Let's say, so I take a high-dimensional space. How high? 2-dimensional space. OK? 2-dimensional space. Let's say, and clearly you see that there is periodicity here, right? Let's say that in each point in which these lines meet, there's a mathematical point. Okay? It means a point with no dimensions. Mathematical point in each intersection. OK, and it is periodic, and it's 2 dimensions. We agree to that. Now, what we do is we make a cut. We create this strip. We start in 1 atom here, or 1 lattice point here, and 1 atom here. and we send this strip here. But we don't just send it into any direction. I choose the direction in such a way that the tangent of alpha is the irrational number tau, which is the Fibonacci number, tau or phi. So this is the tangent of alpha, and it's an irrational number. Aha. What does it mean? It means, be with me, that this line will never, ever meet any other point. Why so? Because if it met another point, then the tangent would be a rational number. Let's say, for example, that it meets this point here. It looks like it meets this point here. It doesn't, but it looks like. So the tangent will be 11 divided by 7. It's a rational number. But I send it into an irrational number. It will never meet any other point. OK? Fine. So this is the cut. What about the project? Now we choose all the lattice points that are within the cut, all these, and we project them onto the one-dimensional space. OK? We project them. This goes here, and so on and so forth. And now let's see what we have. We have large distance, small. Large, large, small, large, small, large, large, small. We have created Fibonacci series. What did we do? We took a two-dimensional space, which is periodic, made a cut, made projection, and from a two-dimensional periodic space, we created a one-dimensional quasi-periodic space. So now, if you have some time this evening, you can take a six-dimensional space, do it at home, and cut and project it onto a three-dimensional space, and you have created a new quasi-periodic order. Is there a crystal like that? Maybe yes, maybe no. But you have created a quasi-periodic crystal. It may be only if you have time this evening. OK. So now that you understand this, let us understand one more thing. Here I do it again. You know this. This is the cut. And alpha, the tangent of alpha is a Fibonacci number. And now I bring in red lines. The red lines are approximately like the black lines, but not quite. They are not exactly. See? They diverge. I made this line, the red line, such that it will meet this point here. So the tangent is, you can count here, it's 11 divided by 7. This is the tangent. Tangent of alpha, the red alpha, is 11 divided by 7. And it is periodic. So this is the period. See, from here to here. This repeats itself. It's a large period. It's a large unit cell if you go to atoms, a large unit cell, but periodic. There are materials like this. Many materials are like this. They are approximately quasi-periodic, but not quite. And usually they have large unit cell. We call them approximants. They are proud to be approximately quasi-periodic. And they have interesting properties. And many people study them. Many people study quasi-periodic lattices. Other people study approximants. These are large unit cell. OK. Now, enough thinking. Let me tell you about the story. And I'll tell you about years of rejection. When I started to talk about my discovery in the corridors, the reaction was mixed. Some people, like John Kahn, were encouraging. Say, John Kahn said, Danny, this material is telling us something, and I challenge you to find out what it is. This was encouragement. He didn't solve the problem, but it was encouragement. Other people, like my group leader, another person, came to my office one day, smiling sheepishly, putting a book of X-ray crystallography on my desk, and he says, Dr. Shechtman, please read this book, and you will understand that what you are talking about cannot be. And I said to him, you know, let me tell you something. My material is not in the book. Took the book back, came back several days later, and he said, Dr. Shechtman, you are a disgrace to my group. Please leave my group. I cannot associate your name with mine. So I left his group. Now, it was not so terrible as it sounds. I didn't have to leave my office or to leave my laboratory, but but instead of reporting to his secretary, I reported to another secretary of another scientist who adopted the scientific orphan, and life came back to normal. But this was the negative reaction. So something between encouragement and totally negative, and everything was somewhere in between. Okay, so if you want to see how I felt during this time, and this was before the publication, 1982 to 1984, I felt something like this. That ended partially in 1984 because as of 1984, I was not alone anymore. So this was a major change. And the growing community of supporters grew very fast. So you would see that now everything is fine and dandy. Not so, because from 1984 to 1987, the major obstacle was the International Union of Crystallography, because they said the following: forget about that electron diffraction. We don't accept these results. Bring us X-ray diffraction pattern for one quasi-periodic crystal. Then we can talk. We could not do that. We, now the community, could not do that because our crystals were very small, were micron size. But in 1987, colleagues of mine in France and in Japan managed to grow large enough crystal. Large enough is like a speck of dust that you can feel between your fingers. You can hardly see it. 1/10 of a millimeter is good enough for single crystal X-ray diffraction. We didn't have that. We had micron size, not 100 micron size. So now we had them, and they sent me the diffraction pattern. I went to Perth, Australia, to the annual meeting of the International Union of Crystallography and presented my results, not mine. These are my friends' results. And this was the picture that I have shown them. Beautiful Laue X-ray diffraction of a single quasi-periodic crystal. See the 5-fold rotation symmetry? See the petal? 1, 2, 3, 4, 5. 3-fold, 2-fold, beautiful pictures. And when I showed these pictures in Australia, the community says, okay, Danny, now you're talking. They have created a committee that redefined crystals. And you have seen the redefinition in the beginning of my talk. So you think, okay, now the International Union of Crystallography, this hardcore body of mathematical crystallographers approves quasi-periodicity. Who will object? Not so fast. Because then there was Professor Linus Pauling. Now, Professor Linus Pauling was probably the most eminent chemist of the 20th century, definitely in the United States. He was the godfather of the American Chemical Society, really an eminent scientist. He taught us many, many things. We studied his books. One thing he lacked, he was not humble. He thought that he knows everything. Well, let me tell you a secret. Nobody knows everything. And neither did he. He claimed that my crystals are twins in periodic crystals. He created models of approximants. And now, when your model is larger and larger and larger, you get closer and closer and closer to being quasi-periodic. But you can never get there, because if you think only in rational numbers, you can never get an irrational number, as close as you go. So this was his major mistake. He rejected my results for 10 years, from 1984, the publication year, till 1994. In 1994, Professor Pauling died. Now, Professor Linus Pauling, I'm sure that some of you have seen him. I had met him several times. He was a flamboyant speaker. He stood on great grand stages saying, Danny Shechtman is talking nonsense. There are no quasi-crystals, just quasi-scientists. When we started this argument, he was like the sun in the sky, and I was about 1 millimeter on the floor. This is how we started. But over the 10 years, it shifted. Slowly, slowly. towards the end of his life, he couldn't publish any paper anymore on quasi-periodic materials. Nothing was accepted. Everybody knew that he was wrong, except for hundreds of thousands of supporters from the American Chemical Society. But after his death, that was the end of opposition, and that was the end of that. Okay, so this is Daniel's pollen. Towards the end of my talk, I want to mention a few people who made seminal contribution. I mentioned Roger Penrose and Alan Mackay. Two-dimensional quasi-periodicity. He did a diffraction pattern to show that it will give you 5-fold rotation symmetry diffraction pattern. Ilan Blair, Denis Gratias, and John Kahn wrote the papers with me. And Dov Levine and Paul Steinhardt are the two guys who proposed a tiling model based on Penrose. While Ilan Blech's model was a physical model of icosahedral joining in space, they produced a mathematical model of Penrose tiles, three-dimensional Penrose tiles, and this is a mathematical model. All these people made a great contribution to the field in the very beginning. Okay, if you want to see what happened during the first years and had the feeling of an exploding field, look at this drawing. It was made by a colleague of mine on a piece of paper, handwritten, not precise. And what he did is the following. And once you understand this, you will see the picture. Here we have the year. The year is 1986, and this is the month, January, February, March, April, and so on, July, August, September. Here is 1 over n. What is n? N is the number of pages in the bibliography. I have to explain. We collected every paper on quasi-periodicity, and we hired a secretary to file them. So she filed them in a filing cabinet, and she put on pages in the computer the name, bibliography. Okay, she made bibliography pages, and n is the number of the bibliography pages. So let's say that there are 20 articles on each page. So when n equals 1, we had 20 papers. When n equals 10, we had 200 papers, and so on and so forth. Okay, so now I understand. This is 1 over n. So when 1 over n is 0.10, it means that we had 10, that n is 10. That means 200 papers, okay? And the number grows as we go down here. So this is what he did. He just counted the number of papers in February, in March, in April, and so on. And as a good, and marked these x's, and as a good scientist, he put them on a straight line. And to our horror, we have discovered that in December of 1986, the number of publications on quasicrystal will reach infinity. That didn't happen. But the feeling was so fantastic that the field is really exploding around us, really exploding. Okay, enough of that. While before we knew that order was synonym to periodicity, now we know that order can be periodic, quasi-periodic, and we are open to new discoveries. And the community was not open before. We are more humble. Look at the new definition of a crystal. Okay. Before letting you ask questions, I will ask the first question, and I will also answer that question. Okay? And the question is, why is it that quasi-periodic materials were not discovered for 70 years? Why did it have to wait for me? I mean, is it because they're very rare? Or is it because they're not stable? You touch them, they disintegrate. Or are they difficult to make? Or are they made of rare elements? Praseodymium, gadolinium, and a touch of zinc? What is this? Why did it have to wait 70 years? Let me give you my answer. From now on, it's subjective. Are they rare? Not at all. There are hundreds upon hundreds of quasi-periodic structures. All of them were studied. Their properties were studied. There are thousands upon thousands of papers, 10,000, 15,000 papers were published on these materials. They are very abundant. No, this is not the reason why they were not discovered before me. Are they not stable? Well, many are not stable. What does it mean? It means that when you heat them up to about 400 degrees C, they will transform to a periodic phase. But below that temperature, they are stable, quasi-periodic. So, and there are many who are stable. Stable means that if you heat them up, they melt congruently. They melt without any phase transformation in the solid phase. right? In the solid state. So the many stable. This is not the reason they were not discovered before me. Okay. Are they difficult to make? And I, with my magic touch, made a few. Not at all. They're very easy to make. You can make them by casting, by rapid solidification, single crystal growth, electrodeposition, CVD, PVD, any method you make, any materials, you make quasi-periodic material. Easy to make. Very easy to make. Are they made of rare elements? Not at all. They're made of iron, aluminum, chromium, copper, titanium. Millions of tons of these elements are used every year. These are the simplest materials available, abundant. This is not the reason they were not discovered. So why it took so many years to make the discovery? Let me give you now my answer. First of all, they had to be discovered by TEM, transmission electron microscopy. You could not discover them any other way. If you had a polycrystalline quasi-periodic material and you took a diffraction pattern by X-rays, you would get rings. You miss the rotational symmetry. If you don't see the rotational symmetry, then you don't know what you have. Many of these phases were studied before, but they were studied by X-ray diffraction. So if you look at the phase diagram, it says complex phase. Nobody could understand what they were by X-ray diffraction. So he took a TEM. So you say, okay, big deal. You are an electron microscopist, very nice, but there are thousands upon thousands like you. Why you? Well, condition number 2, you have to be a professional. That is not so simple. Because to become a professional electron microscopist, you have to know the theory, you have to know what's possible and what's impossible. You have to accumulate hundreds upon hundreds of hours on the machine and know the theory very well to the extent that you can teach the subject to others. Then you are a professional. An experienced, veteran electron microscopist, there are not very many like this in the world. The number shrinks. Okay, so but there are thousands like this, right? You have to have tenacity. This is very important. Tenacity meaning be like a Rottweiler dog. You bite, you don't let go. You discover something interesting, don't just file it in the drawer. Try to understand what it is. I'm talking to the students now. And let me give you a counter example of a person that saw my diffraction pattern years before me. It's a fellow that I met recently. We knew about each other, of course. But we met only recently in Europe somewhere. Here's the story. His professor, one of the leaders of electron microscopists in Europe, looked at the pictures that his students took years ago, or years before that year. And the pictures were taken on glass plates. We took pictures on glass plates. He pulled one of them, and this is Danny Shechtman's diffraction pattern. He looks at it, this is it. Looks at the date before me. He calls his ex-student. Hello, my ex-student. How are you doing? Thank you, Professor. I'm fine. And how are you? He says, Professor, you know, you have seen Danny Shechtman diffraction pattern before him, says the ex-student, by now a manager in a large company. Says the ex, oh, yes, of course, Professor. Of course, I know. He says, Professor, why didn't you tell me? Says the ex-student, you know, Professor, if I told you, you would want me to stay for 2 more years on my PhD. He wanted to finish his PhD. Tenacity. You find something interesting, don't let go. All right? And believing in yourself. If you are a professional and you have repeated your experiment time and again to convince yourself that you are correct, then if somebody wants to contradict you, tell him or her, repeat my experiments and tell me what is wrong in my... Don't just tell me it's not in the books. That's not good enough. Repeat, or if you're a theoretician, repeat my calculation. Show me where did I go wrong. What's wrong with my calculation? But telling me that it's not in the book, that's not a good answer. So believe in yourself. I repeated my experiment time and again. And I was convinced that I'm correct, but I'm listening. Nobody Anybody that tried my experiments joined the group immediately. And last but not least is resilience. See, my promotion were delayed. We have a person here who was vice president at Technion at that time. And my promotion were delayed, and one of our professors that didn't like me. Why would anybody not like me? Well, he did not. And he went to talk to Linus Pauling, telling him, Professor Pauling, they're going to promote Danny Shechtman. Pauling said, Danny Shechtman talking nonsense. He's a quasi-scientist. So he wrote immediately to the vice president for academic affairs of the Technion. It's not me, but Linus Pauling, the son of science, is saying that Danny Shechtman is not worthy of promotion. When that vice president received that letter, he said, we promote him. That's it. Because he knew who wrote that paper, or wrote that letter. I can tell you an episode from that time. My promotion up to becoming an associate professor was very slow, very, very slow. Nobody believed in my results and so on, except for the group that joined the party. But then I received my associate professorship in the Department of Material Science and Engineering. A year later, the Dean of Physics at the Technion calls my chair saying, you promote Danny to a full professor now, said the chair. We just promoted him. He said, he's liable to get the Nobel. It would be a shame if he's an associate professor in this university. Promote him. Our chair said, I cannot do that. Said the Dean of Physics, then I will promote him in our department. I'm telling it because of we have somebody who will represent the department. So my chair collected the committee and said, hey, I'm under this threat. What do we do? So they promoted me. It was the fastest promotion to a full professor in the history of the Technion. So it was very slow in the beginning, and then, shoo, it took off. OK. So a couple of nice pictures. This is a picture taken in the scanning electron microscope by a colleague of mine, Anpeng Tsai from Tohoku University. These are quasi-periodic crystals. See the 5-fold rotational symmetry? See the 2-fold here? See the 3-fold? 1, 2, 3. And he painted it artificially to look like the cherry blossom, which they cherish so much in Japan. So this is a nice picture. And what is now, this little guy is my number 10 grandchild, and he's a born microscopist. See? Thank you very much. Thank you.